Okay, so everyone, welcome to our Introduction to Networks meeting for the 10th of November. Just want to real quick, and I know it says Frank because this is actually come in for, used to be Frank Lambert, who is our support folk person who is now actually Michael. But if you didn't know, and you probably should have received this, if you haven't, you will start receiving it shortly. You also receive these emails typically inside of NetAcad at the, up here on the right-hand side under News and Events for Instructors. You'll see there's talking about DevNet, talking about platform updates. So a lot of times the same things that end up in the newsletter end up here. Okay. So again, don't forget, if you see this, these are items, and this tells you about, you will probably just now have students only because you're not yet, you do not yet have the instructor role, but once you have the instructor role, you'll see both student announcements and instructor announcements. But what we've got going on is there is a new version of Networking Essentials 2.0, and that is a class that is below our Intro to Networking class. And so it's a new class that's come out. Well, it's not a new class, it's a reworked version of Networking Essentials that they put out. So be aware that that is there. I'm actually going to put a free self-paced version on Stanley's, what I call our Open Community College page. In fact, if you are interested in any of your students doing any of those, what I call Open Community College pages, I've got under Future Students IT Academy. And I have, these are, by the way, all the classes that we teach online in our IT Academy. But under free classes here, I've got Packet Tracer, I've got Introduction to Cybersecurity, Cybersecurity Essentials, Linux Unhatched, Linux Essentials, Introduction to IoT, and Entrepreneurship. I'm going to be adding here Networking Essentials as a free 70-hour self-paced class that anybody can take. So it is available for that. So you can do that, and you will see that go here. When I put it in here, I'll send out as part of a class email, I'll send it out telling you that I've put it there and give you a link to this page. But if any of your students need to do Introduction to Packet Tracer or any of these other intro classes or modules, they're more modules than actual classes. But you'll see, you got 15 hours for Intro to Cybersecurity, 30 hours for Cybersecurity Essentials. So if you are teaching a class in high school or community college right now, and you just want to throw in a cybersecurity portion, these two together are about 45 hours of cybersecurity stuff that you can do. You don't need to take classes to be able to teach these, and all you need to do is have the instructor role at your academy. And if you don't have the instructor role, I have a short video on my YouTube channel that shows your main contact how to give you the instructor role. So just want to make you aware of that, because that's something new that has come out that is available for you. Quick aside here, make sure again everyone is doing their labs in NetLabs. Most folks are doing a really good job on that now, so make sure you're doing that. When you upload your assignments for packet tracers, please give me both the documents, but also give me the PKA file. Make sure I get the .pka file so I can grade it. And if you will give me a copy, oh, right there, actually that was exactly what I need to see right there. Give me a picture of your assessment items. Typically this one didn't have an assessment items, it just says completed. But if it does have an assessment items tab, make sure you click that and just do a quick snip for me, and that would make life much easier on me as I'm grading. I'm pretty close to caught up on grading for the most part. All right, so with that being said, let's go ahead and jump in and talk about IPv6 addresses. We talked last week about how you shorten these, how you can do away with leading zeros, how you can replace any contiguous set of quad zeros, any one set of quad zeros with a colon, and how you can get rid of, again, I've already said leading zeros, so you can have a shorter. IPv6, like IPv4, does have a couple different types of addresses. One of them is a unicast address. Now that means from one host to another host. So if I'm going to be sending something, I'm actually going to, I believe Ken had a question about this lab here, about pinging between the labs and those things. I'm going to actually pull this lab up and use it. But you'll notice here we've got these different hosts that we've got IP addresses on, and we've got setups for. So actually, let's go to content here. And one of the things it's telling you to do is to put IP addresses on the PCs and IP addresses on the routers themselves. It even has inside of here the ability to put IP addresses on the routers. You have to set that up yourself. So if you haven't set that up, then actually should happen here. We should actually already have IP brief. Hopefully it's loading. Yep, it's already loading the IP addresses. And you'll notice here, show IPv6 and brief. This is the beauty of NetLabs. It preloaded this config for you. So these IP addresses are already preloaded onto the routers. So the .1 for 192.168.12.1 and the 64s are preloaded on R1 for you. So you don't have to do that. Now let's see if it preloaded the switch for you. It may not have preloaded the switch. Nope, it did not. No. And so that's why it's actually giving you inside of here the commands to do SDM, the SDM commands on it. But what I'm gonna do is I'm gonna go into the PC. Let me pull this out here. So I've got this over here, and I'm gonna just go to the PC and assign IP addresses to it. So let's go, we're gonna say yes here. And let's go in and go to right here, open network settings. And we're going to change connection properties. Oh, actually, let's go back. Ethernet and change the adapter options. All right, so there's a local area connection right there. It's a little hard to see because I've got it squished down in this side. If I do show actual size, it'll pop out here and you can see it. So properties, let's look at what our IP address is right now. IPv4, we have no address, so let's put this on here. So it should be 192.168.1.10. It is a 24-bit mask because it's /24, and I noticed they've given you that on the company LAN here. And then we're going to do 192.168.1.1. Your default gateway is always the IP address of the nearest router interface. So right there is that. We don't have DNS, it doesn't look like. Or do we set up DNS here? I think we may set up DNS as our no, it doesn't have you doing DNS. That's fine. So we'll click OK. And so we got that IP address on there. And now we got to assign our IPv6 address. So I'm going to go ahead and say that my IPv6 address for PCA is going to be 2001:DB8:. See, I got rid of the leading 0 in front of that DB8. ACAD:1:10. All right. Sub prefix length is 64. Now for a default gateway, there's a couple things I can do here. I can set it to be the actual IP address of the router R1. Okay, and that's the Unicast address right here. Typically though, however, we set it to what is going to be called this link local address. Now these addresses, and this is something that is weird about IPv6. IPv6 doesn't have just a single IP address on each interface. You'll think about, you very rarely, if ever, seen more than one IP address on any interface if it was IPv4. There is a way to do it. There's a command called secondary that will let you put a secondary IP address onto an interface. It's a very old command that very few people know about. However, in IPv6, you're always going to have a link local address, and those begin with FE80, okay? And they are used for only local communication. That's why you'll notice that the same link local address is used on both sides of R1's gigabit interfaces. So gig 001 is FE80::1, and gig 000 is also FE80::1. That is because that address is only significant on that link. It is a link local address. So that's why on R1 we can use the same one on both sides. Now we could not put FE80::1 onto PCA. That would not work, okay? because then we would have the same link local address on both sides. But we've got it assigned here. So many times we make our default gateway FE80::1. This way, also, if we happen to change our IPv6 addresses, we don't have to change our default gateways on our host. And now what the lab was basically having you do is do things such as this. We do an IP config. We see our IP address here. And IP addresses of 192.168.132.193. What happened there? Did I not save my IP address? Oh, there it is. Sorry, that was a different one. That's the default switch here. Okay. Down here, 192.168.1.10. So first thing I'm going to do now, the command is simply ping, which stands for Packet Internet Groper. I got caught up watching a movie last night called Hunter Killer, and it was about attack subs, and I was like, Mr. So-and-so, one ping and one ping only. But what this command allows us to do, this command allows us to verify that another host is reachable. So when I do ping 192.168.1.1, this says go send out an ICMP echo request and get an echo reply. So I just verify that IPv4 is working between PCA and router 1. Likewise, I can also ping, try this, FE80::1. And you'll notice that I just got a reply from R1's link local address. You also notice that I do have a default or a link local address on my machine too. See this link local address right here? And the way this is established is on Microsoft operating systems now, it's randomly generated in the FE80::something. So in other words, it's randomly generated in the link local address space. But I can also, if I wanted to, I could ping 2001:DB8:ACAD::2. Actually be 1 because it's on the one side there. You'll notice I get a response back. So you can ping with IPv4 or IPv6 exactly the same. And that's part of what they're doing in this lab. Now, these commands here, this is just to give you an initial configuration on the switch. And by the way, the switch by default does not support IPv6. So if you do a config T, the way to make one support it is to do a SDN prefer dual IPv4 IPv6 default. And now, once I reload this router, let's save it. It will now support IPv4 and IPv6. I'll show you a cool thing once it reloads. I'll show you how to paste this config in without having to type it in. But folks, that is pinging from a machine, a host, to the router. Are there questions about that? Now check out this command. This command's neat. This helps us here because we can actually do this. Let's ping 2001:DB8:ACAD::, and let's see, this is out on the ISP, it's actually 200.225. I mean, gig 000. No, it's ACAD. ::1. Let me go look at ISP. So what ISP's got? IPv6 and brief. DB8 ACAD 2001 DB8 ACAD. Let's do this one, 200::225. So ACAD: 200, which would be actually the subnet 200, ::225. Let's see if that works. Nope. So we're not able to ping over to there. So there must be, I don't even have to ask you to ping that across this. Okay. I've actually made a mistake, ladies and gentlemen. I put the wrong IP address in for IPv6. Y'all should have caught this. I was testing you. You'll notice under IPv6, the actual address is ACAD : nope, that's right. So this is the one subnet. Okay, so I am right there. So let's ping, and then this is just the ACAD. Yep, okay. So we go back up and we can ping the other side here, which is : 1. And we're not pinging across the router. So let's check and see if we have IPv6 unicast routing on. Yep, so that is on. Is this the issue you were having, Ken? I know you put this in your lab about this one, that you were having an issue with this particular lab.
Yeah, this helps explain it. Yeah.
Okay, 2001 : DB8 : ACAD : 1 : 1. So that is correct. And we should better ping 2001 : DB8 : ACAD : 2. Okay, there we go. There she's working. And then this should be 1. There it goes. So now I'm pinging R1s 2 and R ISPs .1. And let's see if I can ping that 2001 ACAD : 200 : 226. Nope, and that one's not reachable. And I don't even know if they have you ping that, but in this particular lab, yep, it did not get there. So let's go out to the ISP and see if we've got. Okay, I see one of the issues here. I see that it did not load the loopback. That would have been, yeah, see 225 works, and that is the IP address on the interface. So in other words, I can ping from PCA all the way over to gig 001 on the ISP. I'm not able to ping this 226 because I got to go put the IP address on it like a doofus. Okay. So in other words, I need to go over here and assign to this external. It's an actual PC, so we've got to assign it in order for it to work. So let's go assign this, and we will have it. So change adapter options. And we'll give it IPv4 address of 209.165.200.226/27. So remember, /27, folks, would be 224. Default gateway of 209.165.200.225, which it gives you, which is nice. And then we're going to go to our IPv6 here and put in the address of 2001 : DB8 : ACAD. By the way, caps don't matter. 200 : 226. FE80 : 225 is the default gateway. So now I should actually be able to go over to PCA, hit the up arrow, and 225 will work. Hit the up arrow and change this 226, and 226 will work. So now I have full connectivity. So once I actually put in all the IP addresses the lab asked me to do, I can now ping completely all the way across from PCA to this external server PC. The command, the ping-t command. So if it asks you to do T is just continuous in Windows. That means just ping it until you hit Control-C. So if I do this, you can have it continuously ping, and all they have you do in the ISP is they have you go in here and shut down the gigabit interface to show the ping stops. Okay. And if you ever have a continuous ping going on, and you want to stop it, you can do a Control-C. You also have the options to what are called extended ping commands. Type in ping, this is mainly from the router, but you can also do it from here. So you can change all different types of items about the number of count, how many times you want it to go. So if you didn't want to do a continuous ping, but you wanted to do a ping and you wanted to ping 50 times or 10 times, you can do n space 10. And then now it's going to ping 10 times and stop. So that's what they're showing you here. Is that the other thing that they showed you was a command called trace route. If I do a trace route to 209.165.200.226, in this case it's trace RT on Windows, it's trace route on Cisco devices, and trace RT on Windows devices. What it'll do is it'll send out an ICMP echo request that is has a time to live of 1, and then it will come back and it will bounce back. It will then, once that's good, it will send a ICMP echo request with a TTL of 2, and then it will be able to go through the second router. So now you see it's going across here. It's actually failing because we may not. Is that the right IP address? 291.165. Let's try. Let's trace route to it. Known good. 201 DB. Yep. DB8 ACAD 200 226. Let's see if we can get a trace route there. But that's what this lab was doing. Now the cool thing is this is a really good lab to show us our IPv6 addressing, because of the fact that we do have here globally unique. And you see here, it went across the first hop of ACAD :1::1. Then it's going to go across the second one of 2001 ACAD :, and that's actually, you're going to find out it's actually the 0 subnet. So this is the 1 subnet for the /48 of 2001 DB ACAD, and then it should go across the 0 2001 DB8 ACAD ::1, which will be the 0 subnet, and then it will come back eventually. Okay, but this shows us globally unique IPv6 addresses. It also shows us our link local addresses. So let's go back over here. I hope that helped with the lab a little bit. Okay, but we did see that each one of those had a unicast address, which is a single IP address that is globally routable. Multicast address are also a type of IPv6 address that is one to some. And so that is used a lot of times with routing protocols, with streaming video, with things of that nature. And then we have Unicast, and Unicast is a little bit different because it's one to the first of. In other words, you can assign multiple different devices the same Unicast IP address, and the first one of those devices to see it will respond to the request. Notice there's no broadcast in IPv6. There is an all nodes multicast address, which is kind of the same result, but by default, there's no true broadcast address, which is kind of neat. We're trying to do away with that, the need for those broadcasts. You'll notice that each IP address is a 64-bit that is the prefix, or that would be considered the network portion, and 64 bits that are the interface ID. And those are created in one of two ways. There's a special format called EUI64, or it's randomly generated. And almost everyone's gone to randomly generated now because EUI64 actually used the MAC address of the device and was therefore trackable back to the device. So But now here's one thing, when you start doing some reading about IPv6, it'll throw you for a bit of a loop. There are multiple different types of addresses in addition to global unicast, link local. Okay, we do have a loopback, which you know, our loopback for IPv4 is 127.0.0.1. The loopback for IPv6 is : 1. So if you're on a PC and you ping, let's do a Control C here. Control C. Now let's do a ping : 1. You're pinging the IPv6 stack running on that machine. If I ping 127.0.0.1, then that gives the IPv4 stack running on this PC. So this just tells me that IPv4 is running and working on the PC. This tells me that IPv6 is running and working on the host or the device, the PC. We do have unique local addresses, which are outside the scope of this, but that's basically going to be the concept of an RFC 1918 address for IPv6. They've not really been implemented yet, and I'm not sure they ever will be, because one of the whole goals of IPv6, if you remember, is that we want end-to-end traceability. So why do we want addresses that cannot be routed on the internet for any type of global address or any type of multi-hop address? So here, our global unicast addresses are unique and routable, and currently only the first 3 bits, 2000::/3, are being assigned. Now that just means this: from 2000 to 3FFFF are being assigned for IP address ranges on the internet. This also means that there are quadrillions of addresses available out there to be assigned. So many addresses. And what's happening and what is actually being suggested by the Internet Authority is that when your ISP starts to give you IPv6 addresses, they're going to give you, now remember the first, we put us up here, remember the first 64 bits are the prefix or the network ID. The next 64 bits are the interface ID. Well, the beauty of IPv6 is they made subnetting so easy for you. What they're going to do is they're going to give you a /48. And that leaves, so in other words, there's the hextets /48. That leaves 1 hextet. Okay. You got 3 hextets for the first portion. You got 1 hextet left, 1 16-bit hextet left. That will be the subnet ID. Now, what is 2 to the 16th power? Anybody know? So we take 2, we raise it to the 16th. Okay. 65,536, right? So at your home, currently, what they're going to do, or what's being proposed, is that they will give you a /48 that will give you the possibility of 65,536 subnets in your home. Each one of those subnets will have 2 to the 64th hosts on it. Okay, now think about that one. So let's go in here and clear this. Let's take and raise 2 to the 64th. So each one of those 65,000 subnets at your house are going to have that many hosts on it. Now, that is the current recommendation for how your ISP will hand you your actual IPv6 address when we start handing out IPv6 addresses. Folks, that's insane. Look at that. I mean, look at the number of addresses for 65,536 different subnets you're going to have. Now, the beauty of this is, just imagine if your PC picks a random number inside of here and a random one of these subnets, and then we figure out a way to have it randomly also switch subnets every once in a while, ends up, past the /48. there's almost no scanning tool available, or there is no scanning tool available other than a quantum computer that could scan the number of ports and IP addresses needed to find your host. So the hope is we won't need NAT. We won't need that type of worry because there's nothing that can scan those largest subnets and larger networks. Now, having said that, we'll obviously have it where it would be possible to scan that down the road, but that's what's being suggested. So we got a global routing prefix, our subnet ID, which is just 16 bits, and then the interface ID. And again, here's the link local addresses. These are addresses that are only available on that local link. So in other words, these FE80 up to the FEBF, that's link local. Almost everybody assigns FE80 : something. But the good news is, like on router 1, all the interfaces can be FE80 : 1. All the interfaces on router 2 could be FE80 : 2, 3, so on and so forth. But these link local addresses are used to send routing updates between routers. It's used as a default gateway for the PCs in order to get out. That's great too, because you can actually readdress your global numbers without having to do great changes on your PCs or even on your down the road, your DHCP address pools that we'll be using. And link local addresses can be assigned statically or they can be assigned dynamically. In other words, we're going to use either the link local command to assign it, or we're going to use an EUI64. And we'll show you how to do that here in a minute. So let's look at global addresses. So we want to assign these addresses, the 2001 DB8 ACAD : 1, 2, and 3, to the 3 interfaces on R1. You would just go into the interface and use the command IPv6 address instead of IPv4 address. Put in the address and its prefix. So this tells me the first 64 bits, okay, which in this case are these. The first 64 bits are the network, and then the host ID is .1. Okay, so this, by the way, if you'll notice, this was the 48-bit /48 that was assigned. This is the 1 hexdet for subnets. So this is simply subnet 1. This is subnet 2. This is subnet 3. If I ask you for subnet 4, it would just be .4. If I ask you for 5, 6, if I ask you for subnet 10, that's where things would get slightly different, because subnet 10 would be 2001 : DB8 : ACAD : what would subnet 10 be? Anybody? Who all's here, by the way? Everybody here? Ken, everybody here? Somebody tell me, what would be subnet 10?
A.
It would be A, because remember, these are hexadecimal, so it'd be /64. So that is subnet 10. 11 would be B, on so on and so forth. And so as we move forward, you would just increment it by 1 in that 16-bit space to get your next subnet, which is pretty easy subnetting, folks, compared to what we've been doing. So,
Yeah, that seems a lot easier.
whole lot easier, and just much simpler. The biggest problem we used to get into is on the hands-on test for this particular class, by the way. It used to ask people to use subnet A and subnet B, and people did not know or didn't think about subnet A is literally subnet A, because that's subnet 10, and subnet B is 11. Okay. Now here is the example I showed you. And this is where, now you'll notice they did actually use a globally unique address here. They used a true global address for the default gateway. You can do that. You don't have to use the link local address. It is, however, a best practice to typically use the link local address. So be aware, you'll see it both ways, and either one will work. But this is subnet 1, and this particular host is host 10. And the router has on it the host address of .1. We'll talk a lot more about DHCP with IPv6 and what's called Slack a little bit later. That's in a whole different section of the curriculum down the road for you. So here we go. static configuration of linked local addresses. This is what we do, especially on all of our routers. So we'll go into the interfaces and we'll say IPv6 FE80::1. Now there's a mistake here. I mean, this is fine. You could use this : 1:1:1:2:1. That's fine. I would have just used FE80::1 on all three interfaces. That's me personally. This works fine. Yeah, they just wanted it to match the subnets here. So they're basically saying this is the link local address for the subnet 1, subnet 2, subnet 3. I would have just made them the same on all of them, because remember, those addresses are only significant on that one interface. They have no significance off of that interface because they're a link local address. And then link local is what makes them link local. That, along with the fact it has to be within the range of FE80 to FEBF. So pretty simple. Now, here's the other item that can happen. This is global unique identifiers. We're looking at our message here on how you can actually do dynamic global addresses. Now, we can statically assign them like I just showed you, or you can use one of these methods here. Now, the first method is called SLAC, or stateless auto configuration. That's what SLAC stands for, stateless auto configuration. With stateless auto configuration, what happens is this: the PC boots up and sends out a router solicitation message. The router will see this and will reply with a router advertisement message. And it will say, okay, I am the router. The method we are using is fully stateless address auto configuration. Here's your network prefix and prefix length. Here's your default gateway. Here's your gateway, and here's your DNS if there's anything there that would be there. Now, typically with stateless auto configuration, all you get is the prefix length, and the default gateway address. You do not get DNS information. Okay, you will not get DNS information. Now, that's okay, because it will allow you to at least get a globally unique address and be able to route. There's another method. Okay, so there's SLAC. Again, we send out a router advertisement, and it says, here's the prefix. And then you'll notice the PC created its own random interface ID. In this case, it could use EUI64, which we will discuss in a moment, or a random 64-bit number, which is preferred in this day and age. And the reason being, now let's think about this. Why would you not want your MAC address associated with your globally routable IP address? Anybody, can you think of a reason? Let's imagine you live in a repressive government regime and you are using IPv6. You do not want them to be able to track a global address back to your individual PC. There's privacy concerns associated with it, okay? Because you got to understand, remember, if part of your globally unique address is your MAC address, and you can easily find out the MAC address. Well, if I have your MAC address, I can find out what kind of PC you have, and I can even find out who the vendor is, and I can probably track you down. Remember our discussion of MAC addresses way back when? So that's why we don't like EUI64 anymore. But with SLAC, all you get is your prefix, you get your default gateway, and that is it. But good news is you can get out on the internet. Method 2 is SLAC with stateless DHCP. Now, what happens here is we send out a router solicitation message. We get a router advertisement, which does have, notice the prefix, the default gateway information, the prefix length, and it says then, but guess what? There's this DHCP server over here, version 6, that you need to get your DNS information from. And then this PC, upon seeing that, will send out a DHCP version 6 solicit, and that stateless DHCP version 6 server will send DNS information. So like the DNS IPv6 address of the DNS server, or servers, typically more than one. And our final method is fully stateful DHCP, which says there's a router solicitation message goes out from the PC. The router will say, look, I'm sorry, I'm not handling information. Okay. I'm your default gateway, but you've got to talk to a stateful DHCP server to get your information. And so then the solicit will need to get not only the address, but the prefix and the DNS information and everything you would normally get from a stateful DHCP server. This is exactly the same method. Well, not exactly. This is very similar to the stateful DHCP version 6, very similar to what we do with stateful DHCP version 4. The only difference is instead of soliciting a router solicitation with version 4, we just send out a DHCP solicitation with the Discover packet. So Slack, there's absolutely no DHCP server involved, and the host only gets its prefix, the network ID, the prefix, and the default gateway. Slack with stateless, the router still gives out the prefix length, default gateway, and then sends it to a stateless DHCP server for DNS. And then stateful DHCP, the router basically says, hey, I'm not giving you any information. Go get it from your stateful DHCP server. Questions about these three, because this will show up on the test. I got a question for you. If I use Slack only, how would I get my DNS information on my PC? Anybody know? If you were to use pure Slack, you would have to go in here and manually assign your DNS servers. Because remember, looking at this, Slack does not hand out anything about DNS. So you could actually do this. You could leave this, obtain an IP address automatically, and then use this DNS. Now I'm going to show you this. Let's see if we can't make this thing change out here. Notice now I've got a different IP address. You know, I used to have 2001 DB8 ACAD, and let's see, my address used to be :1::10. Look at my address now. My address now is 2001 DB8 ACAD :1::, and now I've got this long address here, which is a randomly generated interface ID. Because I chose that, I went in here and I set this to be Slack, obtain IP address automatically. Now you notice there's no DNS information at all for IPv6. So this is an example of Slack in action right here. It basically sent out a router solicitation. The router sent out a router advertisement and said, you are on this network right here. And it did that, by the way, by looking at its interface. It looked at the IPv6 address assigned to gig 001, so that router solicitation come over, and it sent that information back to PCA, and PCA now has this this interface ID and this prefix. So you just got an example of it in action. Any questions? Okay. No questions at all. Everybody's good. Hear all, see all, know all.
For now.
Don't know about that, but we'll review it. We'll just review it again.
Okay. Okay. Well, here we're going to look at dynamically creating an interface ID. First off, again, it can just be random, just like this one. That's a random. This is a random interface ID. It has nothing to do with a MAC address whatsoever. It's just randomly picked by Windows to be a 64-bit number. And typically what it actually does is when it picks this number, it does send out an ICMP duplicate address detection ping, basically, to see if anybody has it already. And if they don't, then it will assign it. Now, the good news is, since there's 18 quadrillion addresses out here, and it's pulling one of those randomly as an interface ID, and actually I don't even know what this is, but it's a lot. But there's enough out here that typically when it's randomly generated, you're not going to have any two that will be the same, but it does actually do a duplicate address detection, or DAD, before it assigns it to it. So that's one way. The other way is this EUI64. Now this is a little weird, but you remember the MAC address is a 48-bit address consisting of 24 bits, which is the organizational unique identifier, and then 24 bits or 6hex bits that are the device identifier. So what you do in order to get an EUI64 is you split the MAC address in half at the OUI device identifier boundary. You then put in FFFE in the middle, okay? And you flip the 7th bit, okay? So in this case, you look here, so we break it apart, we put it in binary. We look at the 7th bit, 1, 2, 3, 4, let me go up here. All right, so 1, 2, 3, 4, 5, 6, 7. In this case, it's a 0, so we flip it to a 1. We find out what that is in hex, and that is our interface ID. So FE9947 FFFE, and then 75 CEE0. By the way, typically if you ever see FFFE in the middle of a interface ID, that means it is EUI64. Okay. Now, if that 7th bit had been a 1, you would have switched it to a 0. So it's just you flip the 7th bit. So the whole process again is split the MAC address into 2 pieces at the OUI device identifier boundary, flip the 7th bit, and stick FFFE and hex in the middle, and that gives you the new one. Now, again, very few operating systems are using this anymore because it allows you to track back to individual devices, which is not good. Okay. But if you ever see FFFE and there's a question on the exam, like looking at this IP address assigned to a host, what can you state? I would be pretty confident in saying that this was an EUI64 interface ID. And then here's our randomly generated IDs, which are much safer in terms of security. And it's why Linux and Windows have pretty much gone with this random EUI, a random generated ID instead of EUI64. Okay. Now, link local addresses, same way, you can have dynamic link local addresses. So in other words, this is an example of a dynamic link local address using EUI64. Okay, so I'll go back to my NetLabs and you'll see here, I have a dynamic link local address for this host, FE80:35AB 40AB98E. So in other words, it's using that interface ID that it randomly generated. This %2 is just something that Windows puts in here. So same thing down here. Don't let it confuse you. That's just for whatever reason Windows puts that in there in the output. Okay, but this particular host has a randomly generated interface portion for the link local address. So we can have EUI64 link locals, or we can have randomly generated. Typically, we randomly generate them on our PCs. We don't typically do it on our routers. So, I mean, we can, like if I had not actually put link locals, if we go in here to, let's go back to the router real quick, see if I can't do it real quick. Show, I still show run. If you look right here, you'll see that down on the interface, you'll see how we've set on this particular interface right here, we set FE80::1 to be the link local. If we had not put that in there, this interface would have generated itself a random link local address. It would still been FE80::, but it would have been something besides 1. For instance, it could be something like this. This is an EUI64, or it could be something randomly generated, depending upon how it's set up to do. Typically, it's using randomly generated now. But they're saying it's using by default, it's using EUI. Let's check that because I think that has actually changed. I'm going to go config T at GI 00 By the way, this is why I really like having a real gear. No IPv6 address, FE80:1 link local. Okay. Now let's do a do show IPv6 address. Let's see if it's show IPv6 and brief. Sorry, brain fart. No, it's actually doing it. So it is using the EUI64. I thought they'd gotten away from that. So, but you'll notice here, because this is FFFE, and what I would also show you is this. Let's do a do show int GI0 GI000. You can see the MAC address is right here, 6CDD. So what they did was they split it down the middle, put FFFE in the middle, and then flipped the 7th bit. So they are using, if you do not statically assign it, they're using EUI64 on the router. Okay. So commands to see this: show IP int brief, show IPv6 int brief, just like I showed you, show IPv6 route, and then you can use ping just to ping IPv6 addresses, just like normal. Okay. Any questions on that? Okay. Well, as we said, IPv6 has multicast addresses. So we've got well-known multicast address and what are called solicited node multicast address. And solicited node is kind of like an all nodes. But the big thing here is typically they, well, not typically, they begin with FF02, but FF02::1 is all nodes. So this is kind of the equivalent of a broadcast, because everyone listens to FF02::1, and all routers listen to FF02::2. So we actually look in here, and I won't be able to show that, but they do listen on those addresses. Last but not least, we've already talked about this, but subnetting is so much easier in IPv6. You get a 48-bit global routing prefix, and then you have 16 bits to play with, starting with 0 going up to 65, 535. So here it is: 0, 1, 2, 3, all the way down to C, all the way up to FFFF. So FFFF. So we're not showing subnet 13 through 65, 535, 534. So actually 535, because this is 536 here. But that's all you have to do. It's so simple. I apologize for my phone ringing, folks, but it's part of working at home. And then here we have all the different subnets: subnet 1, subnet 2, subnet 3. Now you talk about wasting some addresses. Think about this. Sorry, folks, that was a neighbor. FedEx left a package at the wrong house. But again, look at this massive waste right here. This is the 3 subnet with this 18 bunches of hosts on it, and we're using it for a point-to-point link. Now, here's what the crazy thing is. Right now, that is actually what they are suggesting that you do, which is insane. But that is the actual recommendation at this point in time. And I guess they just think there's so many addresses they'll never run out. But yeah, that's pretty crazy. Okay. But there's our subnets, just putting IP addresses on it with IPv6 address. And folks, that's pretty much IPv6. It is not that complicated. It's weird. It's different in terms of the way it looks, but it is not that much different than IPv4. The biggest difference is the fact that we do have those link local addresses that are only used for local communications. And also the fact that because those link local addresses, we actually end up with multiple addresses on an interface. We end up with, we end up with both link local and globally unique addresses on individual interfaces. So we end up with something, at least typically this type of setup, where we have a link local assigned on the router interface, and we have a globally unique address that's assigned to an interface. Any questions on IPv6?
Is IPv6 more efficient than v4?
Yes, it definitely is, especially when you look, if we go back up here at, let me get my, I don't know if I even show it. I think it's actually way back up here. It is way back up in here. But in the IPv6 packet here, when we look at the header fields, one of the things they did is you can see this is an IPv4 header. See all these different portions it has, all these fields. We have to think a router has to actually process every one of these fields every time it gets a packet in. Well, IPv6, look at the packet. Look at how much simpler the header is. Because they did that, because they simplified the header, it is much more efficient. So even though it's bigger, even though the addresses are much bigger because you've got 128-bit addresses, it's actually more efficient because the header is more efficient. Which is one of the reasons why we'll eventually move to it. Plus, it's got some abilities to do some things like IPsec and some other things that allow us to do more security features too.
Okay.
Yep. So again, here's an IPv6 header.
Is there a big advantage of using link local addresses as well?
I think the biggest advantage of link local addresses is that you can renumber your network without having to redo everything. If you're using stateless auto configuration, you got to think about all you have to do is change the IP address on the router, and the router is going to then hand out a different global prefix using Slack. So the link locals, because you can always communicate using the link local addresses, you can use that as your router solicitation, router advertisements for Slack, and that will allow you to automatically hand out global addresses. So I do think that's the biggest advantage.
So is there a reason to use a DHCP v6 server?
Not in a fully stateful configuration, really. Now you need it in stateless so that you can hand out DNS information. That's really probably the biggest typical use for it. And you will actually learn how to set that up with setting up the parameters for what's returned in the router advertisement down the road. But you need it to set up your DNS unless you want to statically put that on every one of your hosts. So typically Slack with stateless DHCP is where most networks are going to end up at. Okay. So like I said, we look at this is kind of cool here. Let's look at what we've got. We've got this gig 000 is this 2001 DBA ACAD. So this is the 0 subnet. So if I go to PCA here, and you'll see I'm on the 0 subnet. Okay, so let's go back and do, let me go check this, make sure I forgot to click OK. Click OK. By the way, don't forget to click OK or it won't take effect. And sometimes the other thing I've learned in the real world is you actually have to disable the interface and then bring the interface back up. Okay, and so we got our IPv6 address here. All right, now if I go back into R1, let's see, that's the gig 001, which is on the internal. Let's change this. Let's do config t int gi001, which is our internal interface. And instead of this IPv6 address here, by the way, I'm gonna show you a trick. You can actually do this. You can, well, this isn't putty, so no IPv6 address. 6 address 2001 bb8 colon acad. Can't type, folks. acad colon 1:1/64. Hit the up arrow. Control A, by the way, pops you all the way back to the beginning. Let you do that. Control E drops you to the end. And let's change this to, oh, I put in the wrong thing. Yep, I had to go back. Hold on. :1 ::1. There we go. Make sure that was taken off. So I got it off there. Yep, so gig 001 has no globally unique. So now we're going to put one on it. So control A, get rid of this. And we're going to change this to the C subnet. Okay. Now what should happen now is we can go back over to PCA. We can do an IP config. And let's do an IP config / release. IP config / renew. Didn't let me do that, so let's do this. Let's disable this and re-enable it. And we should pick up via Slack. Oops, wrong thing. We should pick up a C address. Yep, I notice now how we picked up the C network. So the beauty of Link Local is I never had to change the default gateway here, and I was able to renumber my router, and my router would then use Slack to hand out the new prefix to this particular PC. So that's one of the advantages. And think about it, if we're not using stateful DHCP, we don't have to go change all our DHCP pools. We don't have to make, renumbering your network doesn't become a 6-month proposition. It becomes a couple-day proposition versus 6 months. So I think that's the biggest advantage of using Link Local. You have the ability to discover hosts locally on that local link.
Yeah, wouldn't it be kind of a security thing to have a stateful DHCP6 server?
By that is one reason that you will probably see some entities actually implement stateful, is because they want to be able to track exactly what IP address is on what host. So yes, that is something you may see happen. It's just going to be more work for those individuals.
Yeah, no kidding. We've done that in the past.
Yeah, but then again, here's the thing. That goes back to if security is that big of a deal, you really should be using static IP addresses, both V6 and V4. If you're in a high security environment, you really should have static IP addresses and not even use DHCP.
Okay, that's true. That's true.
But again, kind of a good medium there, a good medium in the middle is to do stateful DHCP with IPv6. But your entire security posture is going to determine how things will work in terms of your addressing.
Okay.
So, anybody else have any questions? Very good discussion. Thank you. That was excellent. I'm going to stop my recording.